Hello everybody, I'm Tommaso and today we talk about robot-assisted medical imaging. What is the goal of medical imaging in general? We take mainly three objectives: precision and reproducibility of the imaging process, integration with interventional maneuver, so integration with other processes that have to be conducted by medical personnel, and teleoperation to conduct surgery and other procedures from a distance. Key imaging modalities. We have ultrasound imaging, so robots are used for stable probe control, consistent 3D imaging, and autonomous scanning. Applications include teleultrasound, elastography, and high-precision 3D reconstruction. Endoscopy. Robots stabilize and guide rigid and flexible endoscopes, enhancing diagnostics and interventions. Capsule endoscopy using robotic control is highlighted for its potential in active navigation. X-ray imaging. Advanced robotic systems enhance trajectory control and radiation safety while supporting procedures like cone beam CT and interventional imaging. Optical coherence tomography. Robots aid precision imaging in ophthalmology and microsurgery, supporting tasks like tremor cancellation and rapid volumetric scans. Molecular and microscopy imaging. Robotic systems are integrated with SPECT, confocal microscopy, and Raman spectroscopy to enhance surgical guidance and pathology assessment. Ultrasound imaging. So let's look at this picture here, which illustrates various approaches to scan path planning in robotic ultrasound systems. Path planning is vital for ensuring the robot effectively covers the area of interest, either for diagnostics or interventional purposes. The figure showcases both offline and online methods. Offline planning involves predetermined trajectories derived from a pre-operative imaging like MRI or CT scans. For example, in subfigure A, a scan path is planned manually on MRI data and transferred to the robot by registering MRI to the current setup. Online planning dynamically adjusts the trajectory using real-time feedback, as seen in subfigure E, where live ultrasound images guide the probe along tubular tissues. Each approach balances precision and flexibility. Offline methods are more structured but can be less adaptable to unexpected changes, while online methods enable dynamic adjustments and enhances robustness in the real-world scenarios. These advancements demonstrate how RAS is moving toward intelligent autonomous operations, bridging the gap between human expertise and machine precision. Now this figure here illustrates the process of autonomous colonoscopy intervention using the robotic endoscope platform. This system integrates advanced modeling and control strategies to locate and target polyps in the colon. Let's go through the sequence here. First, manual polyp selection. As shown in subfigure A, the user identifies the polyp on the interface, marking the only step requiring human input. In subfigure B, the REP autonomously captures multiple views of the target polyp for 3D position estimation. Subfigure C highlights how the system reconstructs the polyp's position in 3D space, combining image data and positional feedback from onboard sensors. Pose adjustment. As seen in subfigure D, the REP adjusts its position and orientation to align with the target. Intervention. Subfigures E and F showcase the final step, extending the biopsy forceps to accurately reach the polyp, as confirmed by onboard and external cameras. This process, taking under 60 seconds, demonstrates how autonomous robotic systems can enhance the efficiency and precision of endoscopic procedures. The success of this approach in simulated environments paves the way for future clinical applications. Now let's talk about X-ray imaging. This figure illustrates the image annotation and segmentation process used to train the FluoroShield system's AI for detecting and tracking regions of interest during fluoroscopy-guided procedures. Let's go through each part. Annotation. Subfigure A shows how fluoroscopic images are annotated with key features, such as catheters, guide wires, and contrast regions. This ensures the AI understands the structures critical to the procedure. Binary mask. Subfigure B converts this annotation into a binary mask, isolating catheter bodies with high precision. This step is crucial for ensuring the AI prioritizes objects of interest. 3 is tri-class mask. Subfigure C expands the annotations to include bounding boxes for tooltips and contrast regions, providing a more comprehensive understanding of the fluoroscopy environment. Segmentation results. Finally, subfigure D shows the segmentation results overlaid on an image, demonstrating how the trained system can detect and classify these elements in real time. This rigorous annotation and segmentation process enables the FluoroShield system to achieve an impressive 95.3 accuracy in detecting catheter bodies and significantly improves its ability to track regions of interest dynamically. This foundational step is key to reducing unnecessary radiation exposure while maintaining the clinical utility of fluoroscopic procedures. Now let's talk about optical coherence tomography, which is an important imaging technique in ophthalmology. Traditional clinical OCT requires an operator and patient cooperation to both align and correct for refractive errors. Automating the tasks of alignment and focusing can increase the accessibility of OCT and make it available outside of specialty clinics. In order to automate these tasks, the researcher developed the robotically aligned OCT scanner that automatically aligns and corrects the focus refractive error. Now let's explore molecular and microscopy imaging. First, the figure 1 shows the imaging setup. The mini gamma camera, seen mounted on a robotic arm, detects gamma radiation emitted by radioactive tracers. Its compact design makes it ideal for intraoperative use, providing high-resolution imaging of hotspots. 2. The robotic arm ensures the camera is accurately positioned around the target area, capturing data from multiple angles. The optical tracking system, visible as reflective markers, provides precise spatial localization of both the camera and the phantom. This setup is crucial for accurate 3D reconstruction of radioactive distributions. Calibration of my mini gamma camera. In this figure we see the calibration process. Subfigure A shows a rendering of the mini gamma camera, highlighting its compact design. Subfigure B reveals a cross-sectional view of the camera detection model generated through precision measurement using a radioactive point source. This calibration ensures the system accurately models how gamma rays are detecting, enabling reliable reconstruction of hotspots during surgical procedures. Reconstruction results. This figure presents the reconstructed imaging results. The top row shows projection along the z-axis, while the bottom row shows the y-axis, each image highlighting the location of radioactive hotspots within the phantom. The white circles overlay the ground truth location of the radioactive spheres, while demonstrating the system's ability to reconstruct hotspots with high spatial accuracy and minimal artifacts. These results highlight how this innovative setup combines real-time imaging and precise 3D reconstruction. Addressing the challenges of traditional bulky system, it allows surgeons to visualize and target specific radioactive regions efficiently, improving outcomes in procedures like sentinel lymph node biopsies. Finally, let's talk about the conclusions. Advancement in robot-assisted imaging. Robots have enhanced the precision, repeatability, and flexibility of medical imaging systems. Key benefits include improved ergonomics, reduced dependency on operator skill, and the ability to perform complex tasks such as 3D reconstruction and remote imaging. The main challenges are the integration into clinical workflows, which remains a hurdle, with issues like long setup times and difficulties in patient repositioning. Another one is cost. High cost of robotic systems and concerns about safety and regulatory compliance are critical barriers to widespread adoption. Potential solution: the use of artificial intelligence and machine learning for rapid setup, path planning and optimization image quality, and development of more cost-effective robotic solutions and shared control systems to balance safety and human oversight.